So
yeah, I think we can start now. So it's a pleasure to have Professor Esslinger again with us. So she'll be giving the second part of the lecture. This Bose-Einstein condensates meets cavity quantum electrodynamics. Okay, Professor Esslinger, please.
okay, thank you. So it's a great pleasure to be here again. Of course, I hope to see you all in hopefully not too distant future personally, and I hope that a lot of people of you will join and do research in the field, and I can read your papers. So that's would be really great. Okay. And if you do so and meet me at a conference, remind me that you had been here and that we've kind of met already. Okay, I would like in today's lecture we will do we'll have a little bit more to do in theory, but not much more, and then I will show you how the experiments work and what you know, in my mind, some key experiments have been. Of course, there's the focus on the work naturally that we have done, but the field is rapidly growing, and you can look at recent reviews, and there is a lot going on. Okay, so the setting is the following. We have we looked at, last time we looked at a single atom, and then we were inside a cavity, and we looked at how you have to treat that. And now we will look at a whole ensemble of atoms, and specifically a Bose-Einstein condensate inside a cavity. And we will look at mostly at the following configuration: that you have a pump beam, a laser beam from the side, which is back reflected, and which is off resonant with the atomic transition of the BEC, so maybe 785 nanometer, and then the atomic transition is 780 nanometers, and it is close to the resonance of a cavity mode. So that is the setting. And we will at this point now try to simplify to get the essence of this self-organization and, well, the somewhat surprising mapping to the decay phase transition. So what I will show you is that you can treat this as a spin system, a spin 1/2 system coupled to a cavity mode, which is the decay model. And it is a version of the decay model where you can actually see the phase transition predicted by Hebb and Lieb and questioned by other people, because for very strong coupling, the A square terms were neglected. Yet it was Carmichael who showed in a paper that in an open system you can actually realize it, and I guess the most easy way to realize was the way we did that. Okay, and a key point is the two-mode expansion. So the nice thing about the Bose-Einstein condensate is that it is a well-defined momentum state. It's actually a momentum 0 state, and with the light field, it is coupled to well-defined higher momentum state, and it's actually coupled to one specific one, and that gives you a two-level system encoded in the external degree of freedom. So that in this two-mode expansion, coming from our general Hamiltonian we wrote down last time, we expand in the in the momentum 0 mode and in a superposition of momentum states. We will come in a moment to see where how that looks like in a momentum picture. So the first, I mean, the 0 state, momentum 0 state, you just, for example, take 1 over the length or some volume or 2D volumes and 1 over constant. And the next higher mode is a modulated, cosine modulated, distribution. Okay, and what you have is that the atoms, you pump the system and you can scatter photons, scattering photons from the pump field into the cavity. Scattering of photons between pump field and cavity mode. That couples the two, couples psi0 and psi1. Okay, and now we can all briefly think what in momentum state, which momentum states do we actually couple? I mean, I've drawn almost everything here in momentum space, the momentum space diagram. This is supposed to be the momentum zero state of the Bose-Einstein condensate. And now we are wondering to which momentum states does absorption of pump photon and emission into the cavity, to which momentum states does that couple? That's, I mean, to get an intuitive picture. So you may, I mean, I will of course draw it in a moment. You might briefly think about it, and you may also, you're welcome to write it in the chat. So basically the question is, we have a Bose-Einstein condensate at zero momentum, that is here, and now it absorbs photons either from this side or from that side, or a superposition of those, and is scattering into the cavity. And now that means the atoms are coupled to another momentum state, and the superposition of this momentum state we want to look at. And I'm happy to see. Okay, so then I will draw some. So here. Does that make sense? Yeah, exactly. Wonderful. Okay. Yeah. So the superposition, the correct one is, of course, you can absorb a photon and emit, or you absorb and emit. So you go absorb, emit, and then that you can do in 4 combinations. So you get into a superposition of, oops, that's wrong, of those 4 states. And now you can also imagine that that will give a density pattern. So you have the momentum zero state, and then on top you have this psi1 state, and that gives a density pattern. And in real space, you will see that you actually do Bragg scattering of this refractive index pattern. Okay, so and what we see now in this picture, if we neglect atom-atom interactions, and if we go into the basis that say this is spin down and the superposition of those 4 states is spin up, then we have a Dicke Hamiltonian. And then we have, in addition, a little bit of a dispersive shift, which doesn't, well, is like a constant, which just causes an overall offset, okay? Dispersive shift small close to / below phase transition. When M, that's just a matrix element, it's roughly 1. Okay, and this two-level system, the transition frequency between the two levels, what is that? That one needs to keep in mind. What is this transition frequency? The energy difference between the two states. They have the same internal state, but they have different external states. And the difference in energy is 2 times the recoil energy. And now you see the trick why this is such a nice realization of the Dicke model or the Dicke phase transition, because the Dicke phase transition basically says, well, what is happening if you drive a two-level system so strongly that your vacuum Rabi splitting is as large as the separation between the energies. And here, if you choose the energy difference of your two-level system really small, which here that's in the few kilohertz range, then you need a fairly weak coupling, again in the few kilohertz, to get into the regime of this phase transition. Okay, here we need to fill in that C0 are the bosonic mode operators for the Dicke model, and the total number operator is this. Okay. And okay, the ladder operator, I will just write it down. We need to speed a bit up. These are the ladder operators. And JZ you can also express in terms of the modes. Okay, and the collective coupling strength. So since each atom, I mean, if you couple, you get a collective enhancement, because if you have a photon, each atom can absorb this photon, and that you get the corresponding collective coupling. I mean, like having a huge dipole. That is given by lambda, and the square root of n is the total number of atoms. And what is also important to note is that this Hamiltonian is invariant under a parity transformation. And that's, we will see in the phase transition, that is exactly the symmetry that is broken. Okay, symmetry, and we should write it down. Symmetry spontaneously broken in self-organization. / Dicke transition. Okay, and now let me say a few words to the Dicke phase transition. That was suggested by Hebb and Lieb and Wang and Hio. Hebb actually, that is a nice thing when he turned, I think it was his 80th birthday, and then Lieb was also invited, and and I had the pleasure to give a talk about their phase transition, which was, of course, a bit intimidating because they are, of course, kind of really big names in physics on the long-term scale. Okay, but it was nice. It was very nice. Okay, and they found out that the decay model displays phase transition. And then Carmichael, that is a paper which is also extremely important in this context. He realized that in an open system, you can actually create a model system that that realizes this Hep-Lieb phase transition. Okay, and it's a second order phase transition to a superradiant phase. I mean, in terms of the Hep-Lieb, what they looked at is in the end, imagine you have an empty cavity which is in resonant with a two-level system, and now you put a two-level system in, and then you get the vacuum Rabi splitting over the James-Cummings Hamiltonian. Now you put a second atom in, and then the splitting gets larger, and another atom, and more, and then your splitting gets larger and larger. And at some point they thought, okay, now if the splitting is so large that it hits the ground state, at some point there will be a phase transition that you suddenly have polarized atoms and a photon in the cavity, which is quite a crazy thought. For real two-level atoms in this very strong coupling regime, you would need another term, but you can, with quantum simulation approach, you can realize the original Hamiltonian that Hep-Lieb looked at. Okay, and the critical, you get a phase diagram that is shown here, and let's put the axis. What is along the x-axis? That is the coupling, lambda. That was a parameter I showed you earlier. And obviously here is some critical parameter where the system goes into a superradiant regime, where you have this polarization of the atoms and photons in the cavity. And this is plotted against the temperature. So you have this phase transition also at 0 temperature. And this lambda critical, that is square root of omega 0 divided by 2, where omega 0, that was the difference between the two levels. And that is a non-rotating wave when you take into account the non-rotating wave terms. And the normal phase, there is Jz is 0, so you don't have an you have population only in the ground state, and no light, no field. And in the superradiant phase, you have J plus plus J minus are unequal 0. So you have a phase, you have a polarization, and the field is no longer 0. That is this phase transition. And now we will come to the PowerPoint part of my presentation, where now I show you how one gets there experimentally, and how you relate that to supersolidity, and the most recent work where you look at where you have phenomena, dissipative phenomena, where kind of dissipation drives the dynamics of your system, where you get quite crazy systems that you can create out of well, this simple cornerstone of the decay model. Okay, so I will now switch to the PowerPoint. Let's see here. Okay. So if someone can, what is the order parameter here? Why is the x-axis? Why the x-axis is the temperature thing? No, the y-axis is the temperature. That's plotted against the temperature, and the order parameter is in the kind of out of the plane, and that is j plus j minus is the order parameter. That is kind of the checkerboard density. We will see that you get a density modulation, and that is and that is shown. And yes, the y-axis indeed, the y-axis is the temperature, and the third axis, the order parameter, and we will have that again in a moment, it goes out of the plane of the iPad. And that is, the order parameter is the j plus plus j minus. That is the checkerboard density. Okay. Very good. So it seems that there I can follow on my iPad the chat. That's good. And now let me share. Let me share the screen. Okay. Okay. So let's have this picture again quickly. Okay. This was we had in mind the BC in the cavity, and now let's go from inside out. That is the cavity again. We have seen this picture. And now, how is the cavity inside the experiment? That is shown here. What we have is a magnetic trap, and then we have, let's see whether I can laser pointer, laser color, laser pointer. Okay. Okay. We have a magneto-optical trap. Then we transport into a region where we create a Bose-Einstein condensate. And this Bose-Einstein condensate is then transported in a moving standing wave into this cavity. And remember, the distance between the mirrors was just 180 micrometer. So the focus of this is right in the cavity. And then it's loaded inside the cavity into a dipole trap. And then all the lasers are applied. So that's, and maybe for those who want to build experiments, here you can see how our design looks like. We have, it's a bit exotic design because we have an atomic source with a medium vacuum inside an ultra-high vacuum. So the bigger chamber is the ultra-high vacuum, and then from inside there is a not so good vacuum with a magneto-optical trap, but that gives us very short transport distances. And then there is a cavity here, and the whole system is cooled down to -80 degrees as to get good enough vacuum with all our coils and everything in the vacuum. But it works very nicely. And that's what it looks like from outside, and you see where the cavity is. Okay, and now let's see. This is the BEC in the cavity, 150,000 atoms typically. Cavity length, finesse, we've had those numbers before. And now we shine a laser from the side, and then we increase the intensity. Now let's see what is happening. So we increase, well, there are some references, some additional reference to other people's work, which is important. But nevertheless, let's look now what is happening if you increase the intensity. Okay, so you increase the intensity. That was the horizontal axis in our phase diagram. Okay, you increase, and then at some point, the system kind of decides to form a density wave, a spatial density wave, and scatter light into the cavity. And this phase transition is a competition between zero-point motion and the potential energy gained by the AC Stark shift. That's what it is. And now you can see here, you have the order parameter, that is the level. So the order parameter is now the y-axis. I think that's what there was the question earlier. That's what maybe is the more intuitive expectation for the phase diagram. So you have here the order parameter, and to the right you have the coupling strength. And at a critical point, the system starts to order, and it starts either to order in an even pattern or in an odd pattern. So this here is both kind of an illustration of the density distribution. So there are two types of modulations, either on the even or on the odd sides. You have to think of course, of a sinusoidal two-dimensional pattern. And on this, this is like a pattern in the refractive, in the superfluid refractive index. And now you can scatter light into the cavity from this pattern in both configurations. And the phase transition happens because at first the system tries below the threshold, minimizes its energy by delocalizing. So it has zero momentum and delocalizes. Above the phase transition, the system can lower its energy by coming up with a density ripple, but lowering its energy since there is an additional field in the cavity, which due to its AC Stark shift lowers the energy. So you have this competition between zero-point motion and potential energy that drives the phase transition. And now let's see what is happening. Okay, but if someone would show up on the screen, that would be wonderful. Otherwise, I feel I'm not talking to anyone, so that would be great. Anyone, whether student or organizers. Okay, so what is happening in the experiment? That is shown here. So the experimental sequence is that you produce a BEC in the cavity, and then you switch on the pump field and increase it linearly, the intensity of the pump field. And then you watch the number of photons coming out of the cavity, which is reflects the field. Okay, and that is shown here. So the time axis is here, and the photon number in the cavity is plotted in blue. Okay, so, and then there's also, I mean, if you take a time of flight, though, you first see no Bose-Einstein condensate. Just a Bose-Einstein condensate. And then you increase the number, the intensity of your pump, that is the dashed line. And then what you see there, of course, because you have a pump field, you will get a little bit some Bragg peak. So you see that you have a standing wave along the pump direction. And now you increase further, and then you see in the photon number a sudden spike, so an increase in photon number. And if you that's done here, suddenly switch off your pump intensity and look at time of flight, then you see an interference pattern which corresponds to the self-organized phase. And then you can also check whether that is kind of a well-behaved phase. So here you see you have a time line where here's a pump power again, you increase, you keep it, and you lower it, and then you get into the phase and out of the phase. And this system, if you look at it with a condensed matter point of view, from a condensed matter point of view, then you can look at it as a lattice supersolid. And why a supersolid? The definition of a supersolid is that you have a combination of off-diagonal long-range order, which is basically you have a superfluid, and you have a non-trivial diagonal long-range order. So that's a density order. And non-trivial refers here to the fact that you have a density modulated wave function. Okay, there's a question here. Okay, very good. Very good. So first question is, what is the detuning of the light with the atomic transition? So that is a few nanometers. So probably we did that experiment. Typically we do them at 5 nanometers of resonance. So the atomic, the atomic decay is negligible. And then should I be thinking of this as a position space wave function or a momentum space wave function? Okay, very good question. It is a momentum space wave function. So what is done is in position space, you have this cosine modulation. You have the momentum zero state plus a modulation by this additional cosine kx times cosine kz. So you have a modulated wave function. And now this, if you Fourier transform it, or when you look at its momentum components, then you will exactly see this is the zero momentum component of the BC. And these 4 states are the superposition states in momentum space that we had discussed in the theory part. And these little peaks here, they come in addition, since the pump wave is also periodically modulated. So this is a momentum space picture. How is the cavity length stabilized? Okay, since it's a lattice momentum, by momentum, do you mean crystal momentum? Yeah. So here, yes, here the non-triviality of the diagonal long-range order is a breaking of the C2 symmetry, because you have 2 possible, so that's discrete, so it breaks a symmetry of the underlying mode structure. And here it's a discrete. We will see later that you may also break a continuous symmetry. But here it's a discrete, and that's why the adequate term is a lattice supersolid. So the system can find its structure either on the even or on the odd arrangement. And how is the cavity length stabilized during the experiment? That's a very good question. There is a super weak off-resonant field at 830 or 850 nanometer, which we use just for stabilization purposes, and which has causes a small modulation, small compared to all other energy scales. Very good question. Okay, And now you can look at it, yes, as also as a phase diagram. And this phase diagram is now, you have the pump cavity detuning in the vertical axis and the pump power on the horizontal axis. And the third axis, that is the mean photon number, and the mean photon number is a measure of the order parameter, because the photons are scattered off the density modulation. You can theoretically calculate that you expect the dashed line for a simple model as the transition of as a phase transition. And here in the inset, you can see this diagram is made by increasing the pump power over time. And then, for example, here, this means this line here corresponds to that line. And then you start to see photons, and that is plotted in a color code here. So that's this line. And you see what a nice way we did in the paper. When we had taken the data for the paper, we didn't take the all the power ramp from here to there. So here there was data missing. We wrote it, of course, in the figure caption, but to make it still look nice, we thought, let's use this as an inset. Now it looks beautiful. And at the time we could send off the paper without taking the data again, and it looks nice. I'm still, one has to write it, of course, in the figure caption, but each time I see that, I still smile. But Christian Baumann, who sees this, that is, he then later took another time the whole phase diagram that you can see here. Okay, now one could say, okay, how do I discriminate between the two symmetry broken states? Because it's a momentum space picture, as was mentioned in the chat. And the two states can be distinguished by the phase, the time phase of the light, which is coming out of the cavity, and measured with respect to the pump light. And that we can do in the experiment. So we did an experiment where we measured the relative phase of the field coming out, the scattered field coming out of the cavity to the pump field. And for even, you have 0 phase, and for odd, you have a pi phase difference. Of course, there is one phase free, so you have the difference of the phase between even and odd is pi, okay? And so what we did, so we set up such a measurement, phase-sensitive detection. And then we did the following type of experiment. So we ramp into the phase and out of the phase again, and that is shown here. And we measure this phase. And then we see, okay, if we are in the phase, we have a stable light field phase coming out. And now we do that several times. We go in the phase, out of the phase, in the phase, out of the phase, and so on. And then measure what type of phases do we see, phase differences. And here you see, we go in the phase, have a certain phase, then we go again into it, and then we have a pi difference in phase. So one seems to be even and the other seems to be odd. And then we do several times. And actually we did it kind of 10 times. And then several runs of going 10 times in and out. And then we did statistics on it and looked at what is, how often do you have even versus odd? Is there any preference or not? And if you take all data, then you have a preference for one. If you then take the data and how fast can we do this switching? How fast can we do this switching, phase switching? So here the time scale is in milliseconds. So we go in and out of this phase in this RAM, but we will also come just in a second in where we change the speed of this going into the phase and out of the phase. Very good question. Okay, but if we do it slowly in and out and take all data, then we have a preference of one phase. And then if we, since there can be residual light field scattering, and if we now take all post-select the data where we don't have in between our data sets, if we have a minimal photon number, so the cavity field goes down to below 0.02 photons on average, then we see a fairly balanced distribution. And then we can also do as a function, we can look at it as a function of a sweep rate. So, and that was exactly the question. If we go fast in and out of the field, out of the phase, so we kind of in a Kibble-Zurek manner, we would create a lot of defects. So we go in fast. And then if the faster we go, the better is our balance. The better is even and odd balance, which makes total sense. Because if you're fast, then you're on a higher energy scale, and any residual symmetry breaking field will not play a role anymore. So this seems to be very consistent also with a simple Kibble-Zurek picture for our situation. Okay. Okay, and another thing that you can do is to probe the excitation spectrum. So one may wonder what are, and we've briefly outlined how you can calculate in general. But the question is, what is actually happening? How can you measure the excitation spectrum of this phase transition? I mean, in general, in a phase transition, you expect that a mode is getting weak until the phase transition happens. And in this case, it's the mode that gets weak is the energy difference between your two levels that gets weaker and weaker. So the effective level splitting, so kind of the dress level splitting, gets smaller and smaller. And if it touches zero, then you have the phase transition into your ordered situation. And what we can do to probe this phase transition is we send a weak pulse with a frequency difference compared to the pump pulse into the cavity and look at whether we can excite the systems. We can either watch the photons, but we can also watch the momentum peaks. And we can measure, we can then change this frequency or this delta here. Okay, let's see. And measure, yeah. And these are data where it's shown. Here you see these Bragg peaks, and here you see the photon number after an excitation, and you see here the probe light of the field. And then you can, for the different regimes, so there's here it's a larger detuning, here is a weaker detuning where the resonance is, and you can now measure, change the pump frequency, and then you get a diagram as shown here. So you take different pump powers. So this is the axis, the lambda, and here is obviously lambda critical. And now you take these excitation spectra for different excitation frequencies. So, and they are between 8 kilohertz and 500 hertz. And you do kind of scans down there. And where you hit the resonance, that's where either with the atom data or with the photon data, we make here these data points. And then as we increase the pump power, we see a soft mode coming down in energy, and it comes down to 500 hertz. So that was in the minimum that we could see. And then we see beyond the critical point, it goes up in energy again. And they're also, I mean, in the dipolar systems recently, they have also measured such mode softening, which one can look at. So, well, we called it roton type mode softening, but I expect that in Tilman Faust talk, you have heard a lot about that. Okay, so now you could say, okay, nice, but this is just a lattice super solid. We would like to see a super solid which breaks continuous translation symmetry. I mean, this is of course now a picture that was from Julian Leonhardt, so that who did contribute a lot to the work I will talk about in a moment. What was his kind of vision of a super solid. So you can see that it is somewhat still a bit super fluid, and it's cold, but it also has a periodic structure. Okay, so that's a possible picture of a super solid if you want to imagine it. But the breaking of the continuous symmetry, that means you may want a situation where you do not just choose between two density configurations, but maybe continuously, that the system, the crystal can form at any position. And this, well, is illustrated here by this moving pattern. And this one can achieve by using two cavities. One might at first think two cavities will just give you two Z2 symmetries. Yes, that's true. They give you two possible Z2 breaking of symmetries, but you can enhance the symmetry. And why you can do that, there is a fairly easy way to imagine. You can imagine that if your two cavities couple with exactly the same strength to your atom system, then there shouldn't be an energy difference whether the photon is in one cavity or in the other cavity or in any possible superposition. So you could have more photon in this cavity and less of the photon in this cavity, but that can continuously change. And if they couple both in the same way, if you have the required symmetry for that, then, and the coupling strengths, then you can continuously change the weight. That gives you a continuous symmetry. That's why it does make sense, even in a simple way. But you could also argue, okay, my complex numbers, they are exactly the same. You have the real numbers on the, say, x-axis, and the y-axis, you have the imaginary part, and you can construct any, well, you break rotational symmetry if you represent your your number with an arrow in the plane. It's in the end, it's the same idea of enhancing this symmetry. Okay. How can you make these two cavities? Well, and they are both on pieces. That is a picture of the two cavities. And we have a new setup built a few years ago. And there you can transport the cavity setup into a high vacuum chamber. And it has a gate valve. So you have a load lock chamber. There you can bake out your system and then you can transport it. And I have a little film to show you how that works. There is also some talking in mostly German when we made the film. So well, anyway, so let's start this film. I hope I can start it. Let's see. Yeah. So that is a sledge, which will be inside. This is a vacuum chamber at the time. Now there's, of course, masses of optics around it. That's Julian Leonard, who designed that mostly. Here you see the sledge where this copper thing which goes into the main chamber. That is the main chamber, and there are different contacts also for electrical connections. And now you can fix it with a screw so that it's rigidly held, so that there are not too many vibrations. So that's now fixed, and you can remove now this long rod, and and then it's in the sides chamber. Of course, here it's open. Usually we do it when there is vacuum. And now you can also get it back again. So that's the reversed process. Now you can rotate the screw again. You unscrew the sledge. It moves backwards. And then in a moment you can take it back from the science chamber in the load lock chamber where you can do the bake out. So there you see, so this is really cool. And now it goes into the other chamber. Yeah, there you see, now it enters the other chamber. That's where you can do the bake out when you put a new system in, and you can get it out. Okay, so that is this setup where Julian Leonard and Tobias Donner were the kind of the heads behind it. Okay, so let's move on to the physics of this. And as I said, we have two cavities now, and you have more combinations on how the photons can be scattered. And you have this continuous symmetry. So let's have a look at the data. And what you see here now, these are phase diagrams which are arranged in the following way. You have the cavity detuning of cavity 1 as the x-axis, and the y-axis the cavity detuning of the second cavity. And why the cavity detunings? The cavity detunings, if I change the cavity detuning, I can change the coupling of the atom light coupling. So I have a continuous parameter with which I can change the atom light coupling. And this allows also to find where the atom light coupling of both cavities are exactly the same. And that is exactly the point where you then have a continuous symmetry, where you have this enhancing of the symmetry. And these plots are done in the following way. The light field is ramped up in intensity, and a certain one cavity is at a given detuning, and then the detuning of cavity 1, say cavity 2, is at a given detuning here, and then you you change the detuning of the other cavity, and that's shown here, and then you measure all the time what is the photon field in one or the other cavity. In one cavity it's red, in the other cavity it's orange. And here you see that if you get closer to resonance, which means you increase effectively the coupling, then cavity 1 fills. If you have if you go to another parameter where cavity 2 is much closer to resonance, then you already have filled the cavity 2 when you increase the intensity, and now you change cavity 1, and then you see that at some point the field in cavity 2 breaks down and the field in cavity 1 builds up. So these phases show you can have either field in cavity 1 or cavity 2. But there is also an intermediate regime here on this line where you have the same kind of, this line is more or less the dashed line of where both cavities couple with the same strength. So the question was, can I have a field in both cavities? Okay. And that is possible if you do it in the following way. You have the cavity detunings with the same detuning, or where they achieve the same coupling, and then you increase the intensity. And then what you see is that a field in both cavities builds up, and then you repeat the experiment very often, and you see always similar lines like this, but sometimes more field in the one cavity, sometimes more field in the other cavity, and that result is plotted here in this quarter circle. Okay, and there is a question on 3- and 4-wave mixing effects. There is, of course, an additional term. Once you have a stronger field, you might have scattering from one field to the other. But here we look at kind of the phase transition itself. At that point, these are negligible. But there are, of course, a whole range of additional effects that one can look at. Is there a phase relationship between the two fields in the two cavities? That phase relationship that we will have a look at in a moment. Yes. And depending on this phase relationship, you have a different pattern, and that gives you the relative phase between the two cavity fields, gives you the continuous symmetry, and that reflects in a continuous symmetry in your spatial pattern. That's a very good question. So this is like a coupling between the cavities mediated by the atoms. Yes, yeah. Yes, yeah, cool. Nice. I'm very glad about the comments in the chat. Okay, let's go to the next slide, and that shows you this enhancing of the symmetry. And here, and I mean, it actually goes directly to that question. So you have the two fields plotted here, and you have a relative phase shift, and depending on that, on the intensities of the fields. I was a bit unclear here. So the fields, and I actually might have given a not clear enough answer. Okay, so the fields to the question of the phase shift. Okay, so one has to think it in this following way. The driving field of the pump, that defines with you what your phase is with which the cavity field is driven. And that gives you only, in terms with a flexible phase, only a plus and minus sign, a Z2 symmetry. So the phase gives you only a Z2 symmetry. So that means with these fields, I can be on all of these possible 4 quarters of the alpha 1, alpha 2 representation of the field. Okay, can be positive, negative for both fields. So that's the Z2 symmetry. And now the continuous symmetry is the intensity of those 2 fields. I can have more intensity in this or more intensity in the other field. And this gives you kind of the amplitude of the projection on alpha 1 or the projection of alpha 2. And if you then plot the spatial distribution of the light intensity, then you see this corresponds to a continuous shifting of the interference pattern. And more precisely, and you can look at it as this as a free energy in this Mexican head. Okay, we'll come back to this Mexican head in a moment. Okay, and in the real space, you can look at the interference pattern here at different points of the circle that I'd shown before. And there you see this interference pattern, say you look at this line here that shifts continuously. And the upper line, the lower line shifts just in the other direction, but it's a continuous symmetry. And you can also mathematically look at it to look at the Hamiltonian, and then you can show that there is a U1 symmetry in the system. Okay. And now you can also look at what are the excitations now of this system, which breaks a continuous symmetry. And here kind of there is a Mexican head illustrated, and we had early on seen this Mexican head in the alpha 1, alpha 2 plane. So the nice thing is that if we read out our field, we can directly read out the order parameter and the excitations of the system through the field. Okay, and now let's see what type of excitations can I have. I can have, for example, an amplitude excitation. So this excitation means that the total field in both cavities, if I add up, that they change their intensity, or they are both oscillating in phase, the intensity. Yet there is another mode possible, and that's a Goldstone mode. The previous mode is often also termed Higgs mode, and this is a Goldstone mode. So that's just a phase mode. That is the redistribution of photons or field from one cavity to the other. And that costs almost no energy. And that means you have an oscillation one field with respect to the other. So you could look at it in this way. You can describe it as well as an excitational amplitude or as a phase excitation. And now we can do the Bragg spectroscopy again, as we did with one cavity. Now we can do that for the 2 cavities. We can excite in both cavities, and then we can look at the energy spectrum. And that is what we see, okay? What we see now is, again, the modes, so these are in the two cavities, the modes come down in energy. And then when we go beyond the critical point, we now have two modes. We have one mode which increases in energy again, and that's one would associate with the Higgs mode or the amplitude mode, and a lower mode which is the phase mode or Goldstone mode. Now you could say, okay, but what I see here is two modes. One goes up in energy and one stays low in energy. How should I know whether that's phase or amplitude mode? And the nice thing of our experiment is that we can directly read that out of our photon data. Okay, so for the Higgs mode, you would expect that both fields are modulated or both photon numbers are modulated in time in phase. So that gives you a total change in the field strength. And in the phase mode, one of the fields in one cavity would go down whilst the other one goes up. These are the two modes, and we measure those fields and we can extract the phase, the relative phase of this modulation. And the data that is shown here, so the upper data shows the Higgs mode, and here you see that you have both cavity fields oscillate in phase, and you have the absolute value of alpha is modulated, whilst the phase stays fixed between the two. And here in the lower picture, and that's an excitation with the lower energy because that's this low energy mode, there you see it after an initial decline in energy. Then there you see that the alpha is just declining a bit, but the phase is modulated, and that you can see here. Okay, so that's a rather direct illustration that you have this amplitude and phase mode. Okay, so now we come to another part, and I would suggest that we make a 5 minutes break, and then we have enough energy for a new part. And the new part, I mean, because you can see here, it's driven, dissipative, interacting quantum many-body system. And this sounds so awful because it's so complex, but you will see it's not so complex because one has here something where the dissipation, you can actually associate with the dissipation a very characteristic feature. You can associate a dynamical instability with the dissipation only due to the dissipation. And about this experiment, and that was the PhD of Nishant Dogra, I will talk about the break after the break. Okay, so I will leave that here and I will be back in 4 minutes. Okay, so see you in 4 minutes. Okay, let's start.
There are some questions, Professor Esslinger, if you would like to take them.
Yes, sure. In the chat, or where are they? Because in the chat, I have answered the chat questions. No, there may be, I have not answered all. I've answered the last one. Okay. Okay, the previous to last. Okay, does any of this require a DC or cold gases in the cavity? Or a cold gas is enough? Also very good question. You have also this phase transition in a cold gas, but it's getting more complicated because you don't have the nice two-level system anymore. So and then you have to fight against a thermal energy scale because depending on you now have to think of superpositions of different kind of momentum families, and there you have to form a density pattern. But you can still imagine that in principle, you should be able to form a density pattern also in a thermal cloud, so it will still work. And there has been a very nice paper by Willi Zwerger analyzing kind of the multi-momentum mode, which can then be generalized to finite temperature. I think with Philip Struck, the work was to look at the finite temperature. And there had been work prior to our decay phase transition in Vlada and Vuletic's lab, where they looked at the thermal cloud and could see that there is a form of self-organization. And so this is like a coupling between cavities mediated by the atoms. Yes. And is there a phase relation? That I had already answered? Okay, good. So I think the questions I've answered. And then I'll move on with the dynamical instability. And for this, we have to look at one additional thing. And that is what is happening if we change the spin polarization of our pump laser. And that is illustrated here. And then one could argue, okay, that only is relevant if we also have different magnetic sublevels. But those one can have, and we look at magnetic sublevels MF equals 0 and plus minus 1. Okay, so and now you imagine you change the angle phi of your polarization with respect to the y-axis. Okay, so and let's see what's happening. So if you have normally linear polarized light along the y-axis, as we had done in the previous experiments, then you scatter, well, the atoms, you can imagine they are scattering like a dipole into the cavity. So it couples to the cavity mode. It's different if you drive a dipole pattern along the x-axis that will not couple to the cavity. Okay, but that's not the end of the story. I mean, you can, of course, look at your linear polarized light as a superposition of sigma plus and sigma minus light. And let's assume we apply along the propagation, light propagation direction, a magnetic field. And we look at all three different magnetic sublevels of the F equal 1 manifold at a fixed finite magnetic field. And then we will see that the coupling to sigma minus and sigma plus is identical only for the MF equals 0. And then you could get an oscillating dipole, which will not scatter into the cavity. It's different, however, for the MF equal minus 1 and the MF equal plus state. And those will give rotating dipoles. And they will also give a phase shift in time phase of the light field. And you can also look at it as a scalar dipole moment plus a vectorial component. Okay, let's now look at that. Well, that is basically summarized that if you have MF equal 1, MF minus 1 or plus 1, you should be able to scatter. And now we did that in the experiment. So what's shown here, the normal linear polarized along y-axis, and we look for the, these are the phase diagrams as shown before, detuning versus pumped field, and for the MF equal +1, 0, and -1 a sublevel. And now we change the polarization. And then we see at 75 degrees, we still have fairly, I mean, these phase diagrams on the left, they looked all basically the same. Here, we see that we can self-organize quite easily the MF equal plus and the MF equal -1. Yet, the MF equal 0 is much more difficult to self-organize. You need much more power. And if we go to 90 degree, the MF equal 0, as we had expected, will scatter just in the wrong direction and not self-organize. Whilst the MF equal +1 and the -1 will self-organize. And they will self-organize with different phases of the scattered light. And this phases of the time phases of the scattered light, which one can measure in the output of the cavity, they are shown here. Okay, and if you have a 90 degree phase shift, if you are at a 90 degree polarization. And of course, for the MF equals 0, we can no longer measure because there's no light coming out, because there was no self-organization. Okay, you can also do that in a spin mixture. And then let's focus on the spin mixture of MF equal +1 and -1. And then you get a phase diagram shown like here. So here we have the parameter on the horizontal axis is this angle of polarization. And then we see that we can associate in this regime, if we have an angle below 60 degree, then we can associate what is happening in the system is a density pattern forms. And the density pattern forms in such a way that both MF equal plus and MF equal -1 are sitting on the same sides, on either the even or the odd sides. However, if we go to an angle, say above at 70 degree or something, then we get a spin texture. And then the spin down sits, say, on the even and the spin up on the odd sides, or vice versa. And you can look at that, well, in this way. Okay, so, oops. So you can look at it as light in the vertical direction is a pump light, and it will be backscattered into the cavity, okay? Well, because here there's higher density, there's this modulation in the refractive index. And this is distance here is lambda, so you will constructively interfere. And now, well, you would say if this is just density, then it would not constructively interfere. However, you have the phase shift between the driven dipoles. And due to this phase shift, since the spin up and spin down are 90 degree out of phase, you again get constructive interference scattered into the cavity mode. Okay. However, your mode, you couple with the in these two different situations, you couple with different quadratures of your light field. Okay, so in a simplified diagram, it's the following. You have a Bose-Einstein condensate, which in a superposition of, in a mixture of a spin up and a spin down state. And you can couple this with one quadrature of the light field to the density mode, and the other quadrature of the light field couples to the spin mode. If you go very much kind of in one spin, in one polarization of your driving field, you're either here or in that situation. Now the question is, what is happening if both these modes are getting soft? You're coupled to both, and then they seem to compete. There something must happen. Both are getting soft at a certain angle of polarization. And that's what we looked at. What's happening there? And one would say, oh, these are orthogonal. Nothing will happen. If it comes from that side, it will stay there. If it comes from that side, it will stay there. But that's not the whole story. The whole story is that those two modes are coupled by the cavity dissipation, because the cavity dissipation leads to a phase shift of the field inside the cavity, and that couples those two modes. So the dissipation here leads to a completely different phase diagram, not just to a little shift of something, or but it leads to a new phenomenology. And in the slides you will find, since the time is passing quickly, I think, I will not go through this Hamiltonian. The basic point is you have a coupling to the density mode and the spin mode, and one time the coupling is the one quadrature of the light field and the other quadrature of the light field, and you have with plus and minus the two spins indices. And you have here the density mode as an order parameter, or the spin mode as an order parameter. And you can adiabatically eliminate the phase, and you can solve what you get then when you do that is the following, that you get a regime where your system is in time driven from the density mode to the spin mode, to the density mode, to the spin mode, and so forth. And that's what we also had observed. Actually, we had observed it, and then we needed to think, Nishant thought, and Manuele Landini and the other co-workers, how to interpret that. And here we can see that this motion in between the modes, that pops up in the phase, in the time phase of the cavity output field, which is plotted here. And that is running, and that is shown here. And you can also here see on the left, that is the normal self-organization in the density mode. And here, this middle and the right picture is if you have this self-oscillation between density and spin mode. And here in the middle, it's when you have actually a dissipative kind of a locking between those two modes. And then you can you get this phase diagram, which I briefly had discussed. And here, as a function of polarization mode, here you see the modes and the locking of the modes. And here you see that the mode that is oscillating has a gain. And you can also get into a regime where you have a kind of a limit cycle, where there is a fixed indication of a limit cycle, where we have it's oscillating at a fixed frequency. And one can associate that with mechanical forces. I will just give you, that is the last slide I will talk about. That is the mechanical analogon to what we've seen here. So imagine you have a shaft, that's this outer circle, filled with a hydrodynamic medium, okay? And now you have a disk which is rotating, okay? So the disk is rotating, and that will lead to friction forces with this hydrodynamic medium. And it will leave, if you start rotating at the center, then you have an instability. If you slightly go away from the center, since it's a hydrodynamic medium, you will have a larger velocity here and have a larger friction force here, which will give you a total force, the friction force, upwards. And this friction force is position dependent and not, as we often associate, velocity dependent. And on this previous view graph were the different mechanical forces and how they are categorized. And this position, non-conservative positional force, that is analogous to our in our observation. And what I'm not going to talk about now, which is again a big field of research, is that if you look at a lattice model plus the long-range orders, which is of course super interesting because there you have a competition between the atom-atom interactions. They can be on the same energy scale as the long-range interactions. But that would be too much. And here's a phase diagram. But what I would like to thank here is the current team. Since due to the corona, so that's not the latest team, but you see here that is Nishant, Dokra, then Manuele Landini, both worked on the cavity. And we have also Tobias Donner, of course, he is a senior scientist in my group, and also on the cavity, Francesco Ferri and then Rodrigo. And up here you see the impact team where Tobias Donner and I are co-PIs, and the team of that experiment, that was the two cavity team. With that, I would like to thank you all for joining the lecture. And yes, I hope you enjoy the rest of the school, and I hope that, yes, we will meet in person at some point, and hope that you'll...
Thank you so much, Professor Esslinger. And there may be some time for quick 1 or 2 questions, if there are any, from the participants. I was reading that review article which you suggested in your in your talk, those references, and they sometimes use this confocal cavities, which is known to be unstable. In what context they use this confocal cavities and unstable cavities?
Yes. There is concerning these cavities with many modes. There is work in Ben Leff in Stanford. He is looking at that. And I think the challenge there, it's very nice work. The challenge there is that, of course, if you couple to many modes, you couple weaker to each of the modes. So yes, you are in a regime, well, where you have to compromise a bit more on other heating rates. But I think it's a very interesting approach to look at several modes, and be it, well, there are different ways how you can produce many modes, but surely that's a very interesting approach. Yeah.
There's another question from Saikat. So it's in the chat box. You can look at the chat box.
Is the cavity output oscillation N equal between the SM and DM phases? Are also due to these being super between, is the cavity output, I need to understand what's been asked. Output oscillation N between the...
Yeah, maybe I can ask directly. Yeah, I think that
was
the typo that might create confusion. So I was asking that when you detect from the cavity, the SM, the spin, and the dissipative modes, are they like super and subradians, and that is why you see the cavity, that oscillation? Are they like super and subradians, and that is why you see the cavity, that oscillation?
So I'll go back. Maybe let's see.
Now, let me rephrase the question. What Saikat is asking that those two modes, spin mode and the density mode, yeah, can you consider them as the subradiant and superradiant states? Is that the question, Saikat?
Yeah, that's the question.
Okay. I guess that's the question. Let's see whether you can rephrase it. I need to think whether the rephrase. I have a problem here with my. I think my computer is.
Okay. What I suggest, Saikat, you can get in touch over email with Professor Esslinger and clarify this point. Okay. So let us thank, since because of constraint in time, let us thank Professor Esslinger for excellent lectures. And we do hope that in future activities you would be physically here, or at least online. You'll be joining us again in future. So looking forward to all that.
Yeah,
thank you.
It was a great pleasure. Thanks very much for the invitation, and I think it's great that you organized this whole school. I think that's really, really great. And I saw also that the community, that so many people joined in. That's really great.
Yeah.
Right.
Thank you.
Okay. Thanks a lot.